Traditional RAG systems work by indexing raw data. The data is simply chunked and then embedded and stored in a vector DB. Whenever a query comes in from the user, we normally send it to the vector DB and then get the response back. As this retrieval step happens for every single query from the user, it is the most critical bottleneck to speed up a naive RAG system. So would it not be logical to make the retrieval process super efficient? Now, this is the promise of LightRAG. Now, before we look into the LightRAG, you may ask that we already have GraphRAG, so why do we even need a LightRAG? The answer is that the GraphRAG uses LLM to process the entire private dataset, creating references to all entities and relationships. This graph is then used to create a bottom-up clustering that organizes the data hierarchically in semantic clusters. So what this means is that whenever you have new data, then you will have to go through this step all over again over the entire private data set, and this is going to be a super bottleneck. That is where the LightRAG comes into play. The biggest selling point of LightRAG is the fast adaptation to incremental knowledge base. Whenever you have new data, LightRAG incrementally updates the knowledge base without the need for complete reprocessing of the entire database. So that is one advantage of LightRAG. The second selling point of LightRAG is its computational efficiency itself. In terms of the cost, in terms of the tokens and also the API calls, compared to GraphRAG, we can see that LightRAG uses less than 100 tokens in a place where GraphRAG is going to use 610,000 tokens. And in terms of the API call, GraphRAG is going to do too many API calls during the retrieval phase, where LightRAG is just going to do one API call. So these are the main advantages of using LightRAG against GraphRAG. So you're going to get a super efficient retrieval system. But how does LightRAG achieve this feat? So LightRAG achieves this feat using two techniques called graph-based text indexing and dual-level retrieval paradigm. So let's look into graph-based text indexing. Let's take an example document about honeybees and beekeepers, etc. First step is that of the entity relationship extraction, which is represented by R here. So this step ensures that simple entities are first extracted from a given document. For example, beekeeper is an entity and bees is an entity, and the relationship between them is observed. So in the first step, it ensures that the ER is extracted. In the next step is the key value pair generation using LLM. So this is where it employs an LLM. We basically pass the extracted entities to the LLM and we do what is called LLM profiling, where we actually get a description from the LLM. It's very similar to how LLM would answer about anything that we ask. Third step is deduplication, which is represented by the D here. Because we will have multiple chunks in the database, and because all of them are going to talk about, beekeeper and bees and honey, we might have the beekeeper entity extracted multiple times. So the deduplication step makes sure we just have one and it's going to eliminate the rest of it. And once these three steps are over, it is going to give us a graph which represents the index graph used for retrieval. So this graph is going to be used whenever we want to retrieve any information based on user's query. Dual level retrieval is nothing but two levels of retrieval. So one is low level retrieval, which needs to address the specific informations. And then there's high level retrieval, which needs to address concepts and summaries. For example, for the specifics, the user may ask how many queen bees can be there in a hive. And for the high-level retrieval, the question might be, what are the implications of climate change on honeybees? So these are like two levels of questions, basically, and the system should be ready to address questions at these levels. So if we look at the figure that they have given about dual-level retrieval paradigm, we can see that there are high-level keys, for example, agriculture, production, environmental impact, and there are low-level keys, such as beekeeper, honeybee, hive, etc. Whenever a user query comes, LLM extracts both the high level and low level information and it puts it together and matches with that of the user query and then tries to answer. So the answer is much more relevant to what the user is expecting. So one thing to note here is that this LLM is more of a general purpose LLM, and this LLM, in my understanding, is different from the LLM that's used here for profiling. That's what they mention here as well. If we look at the utilization of retrieved information, they say that LightRAG employs a general purpose LLM to generate answers based on collected data. Now you may be wondering what's the implication of employing an LLM here, because we are going to be using an LLM during the indexing phase. But they are saying that this is going to be a trivial operation, as we're going to be using the LLM to extract entities and relationships for each chunk. And the LLM only needs to be called total tokens by the chunk size times. So this is going to be a trivial invocation operation. For example, if you have 1,000 tokens and if you have a chunk size of 100, then the LLM is going to be called only 10 times. So there is no additional overhead involved in this process. So they're defending against employing an LLM in the indexing phase. And when it comes to graph-based retrieval phase, they're saying that instead of retrieving chunks as in conventional RAG, they concentrate on retrieving entities and relationships. Thereby, they are simplifying the retrieval process itself. And this approach markedly reduces retrieval overhead compared to community-based traversal method used in GraphRAG. This is a big selling point with LightRAG. Now that we are seeing the architecture and their defense against the usage of LLM in the indexing phase, and also their approach to kind of retrieval, let's see how it performs. Let's look at the evaluation and find out how well LightRAG performs against some of the state-of-the-art methods. They have compared LightRAG with 3 others, which is the NaiveRAG, RQRAG, Hide, and GraphRAG. And they have also tested against these 4 data sets, which is agriculture, CS, legal, and a mixed data set. And in each of the cases, they've clearly highlighted that LightRAG, as underlined, shows better performance against the compared other 3 RAGs. So for the comparison, they have used GPT-4o Mini as the LLM, and they've also fixed the chunk size to 1200 for all of the data sets in order to keep the comparison fair. For evaluating, they are looking at 4 dimensions for evaluation. So one is the comprehensiveness, where they look at how thoroughly does the answer address all aspects and details of the question, and the diversity, as in like how varied and rich the response to the user's question is, and also empowerment, as in how effectively does the answer enable the reader to understand the topic and make informed judgments, and overall, where they check the cumulative performance across all of these 3 dimensions that they are evaluating against. So that's pretty much it. With that evaluation, they just wrap up with a few ablation studies. For example, they find out how it works when you just have low level only retrieval, or if you just have high level retrieval, what happens. And then they talk about hybrid mode, which is that in a full version of LightRAG, combining the strength of both low level and high level retrieval method. And they also show some case studies, which provides a clear comparison of the baseline method with that of LightRAG. But we have covered pretty much the main idea, which is that of graph-based text indexing and also dual level retrieval paradigm. That's pretty much what I wanted to say about LightRAG. And with that, I'm wrapping up, and I will see you in my next video. Until then, take care.